Your Stodium.
Who wants to throw it in?
I go. Oh, jeez. Catches on fire and then it explodes.
I have some good friends in the nuclear industry that are very big advocates of the fast breeder reactor. The common name for it now is the integral fast reactor. Personally, you know, I'm not the biggest fan of a reactor that's full of liquid sodium.
It's stored under an oil to stop air or moisture getting on it. Reacts very, very quickly with air and also with water. Well, the hydroxide is a white crust on the outside. It's fizzing around as it's generating lots and lots of hydrogen gas. And see now the heat from the reaction is burning away all of that hydrogen.
You don't want to build a reactor out of stuff that wants to burn, react, anything. You want to go, whatever I've made you out of, I want it to be like the rock bottom of stability. I don't want there to be no step further down that is chemically favorable, because that's how things burn. The fast breeder guys use sodium because it doesn't slow down the neutrons. And everybody who was pushing plutonium said, we want a fast reactor. That's the only way to do it.
The notion of the public being intimately involved in very complicated technical issues which went way beyond the competence of any member of the public, it just didn't seem that that was the right way to do it. And I think the basic question is, can modern intrusive technology and liberal democracy coexist? The decision of what is acceptable is not something that we technologists can make. It's something that the public makes.
I think a lot of people were daunted by nuclear energy. Oh, there's no way we could learn this stuff. I don't want to do that class. It's going to be too hard.
These three coolants are generally associated with three different nuclear fuels. Liquid sodium-cooled reactors are fueled by natural uranium. Water-cooled reactors are fueled by enriched uranium. And molten salt reactors can be fueled by thorium. The reactors deployed commercially around the world are water-cooled. Today, we use water to cool reactors because we use enriched uranium as fuel. And we use enriched uranium as fuel in today's reactors because they are water-cooled. Despite sodium's reactivity with both air and water, it is in some respects a safer coolant than water. This is because our enriched uranium-fueled water-cooled reactors pressurize the water to raise its boiling point and drive steam turbines more efficiently. If we didn't pressurize the water, then we'd be using much more uranium and producing much more nuclear waste per watt of energy.
In addition to being a thorium guru, Weinberg was also the original inventor of the pressurized water reactor. So it was a little bit of a tricky thing to have the inventor of the light water reactor advocating for something very, very, very different.
As long as the reactor was as small as the submarine intermediate reactor, which was only 60 megawatts, then containment shell was absolute. It was safe. But when you went to 1,000 megawatt reactors, you could not guarantee this.
Weinberg never really was crazy about the light water reactor. He didn't like the fact that it had to run at really high pressure. He figured there would be an accident someday where you were not able to maintain the pressure or keep cooling it.
In some very remote situation, conceive of the containment being breached by this molten mass.
A small valve in this collection of pipes is stuck in an open position, letting steam and water escape from the reactor core. It's critical that the uranium fuel rods that make up the reactor core stay underwater. A yellow tag covers an important light. They're convinced that the core is covered by water. A huge bubble of hydrogen is forming right inside the reactor vessel.
The hydrogen was generated by reaction between air and the zirconium fuel cladding, and then that hydrogen ignited from some sparks.
Boom! The whole building shudders. I mean, the whole building, the plant building, boom! And somebody says, what was that? An explosion had taken place inside the containment building.
And those gaseous fission products came out and were released to the environment.
Pregnant women and preschool-aged children leave the area within a 5-mile radius.
It took a month to shut the reactor down. But finally, Unit 2 was stone cold dead.
It was the biggest environmental release at 3 Mile Island was krypton and xenon, but they don't have an uptake in the body. It scared a bunch of people, but it didn't hurt anybody. It really comes into which fission product is it. I know that sounds particular. Number one, most dangerous is iodine. because of the way it's taken up by the thyroid.
There was a metallic taste in our mouth, an acidity. They say radiation has no taste. It was only later we realized it was the taste of radioactive iodine.
Chernobyl was just a bad design in the first place.
Koryakhin and a fellow engineer wrote an article in the newspaper Communist. It criticized the lack of safety in the design of the plants.
They had these cylindrical graphite followers, they called them, that kept the water out of the place where the control rod was in the core. Well, they pulled it out so that the follower was out of the core too. Yeah. So now all of a sudden they had water turning to steam and the pumping system cavitated.
Power's rising, Alex. Power's rising.
Well, he put the turbine in. How's that? He was stable just now.
Come on, we've had this. Let's stop it.
Come on, Alex. Let's get the rods back in. AZ, shut down the reactor.
I'm putting the controls back in. AZ, sir, I'm shutting down the reactor.
Well, there goes the test. How am I supposed to explain that? I'm sorry, sir. It wasn't worth it. The power was climbing. I didn't know exactly how it was coming.
What was that?
The rods haven't gone in.
Let them drop in.
I am doing. I just don't know why they didn't go in the first place. I pressed the AZ button. They should have gone in.
Maybe.
A series of detonations go off in the core of the reactor.
The explosion had thrown the 2,000-ton reactor lid in the air. It fell on edge into the mouth of the reactor vessel. Pieces of the core were scattered all around.
The core just burned for days. A lot of radionuclides were released to the environment.
The white flashes on these images are the results of radioactivity on the film. People in the streets hardly blink an eye at the masked soldiers scattered throughout the city.
At first, I was told there hadn't been an explosion. The consequences of such false information were particularly dramatic.
Windows and doors should be sealed and iodine tablets swallowed to counteract the effects of radioactivity. Yet no such orders have been given.
Taking potassium iodide can help the thyroid not absorb radioactive iodine. It prevents your thyroid from taking up the radioactive stuff because it will be plumb full of the not radioactive kind.
30 hours after the explosion, more than 1,000 buses arrived. The army announces the city is to be completely evacuated.
It exploded when you hit the AZ button. Why didn't it stop the reaction? You say there couldn't be a design fault, but how else do you explain it?
They'd know. And if they knew, they'd tell us.
They weren't aware of the facts. The potential neutron surge as the graphite tips re-entered was a known problem. Known by whom? Nobody told them. Nobody. The control rods are made of boron. But they're tipped with graphite. Now, in '83 at Ignalina, on a similar reactor, we found that in certain circumstances, when the graphite enters the water, it causes a power surge. A power surge.
If you do stupid designs, something bad will happen even after 40 years. Because a friend of mine was GE's first nuclear safety engineer, and he worked on the Fukushima plant, and they would have meetings with the TEPCO officials and engineers, and they would all nod their heads in long meetings and say, oh yeah, we'll do this, we'll do that. And then they go off after the meeting and do whatever they wanted. And that's why you had a 15-foot seawall with a 45-foot wave coming over it, and diesel generators and fuel in the basement.
The earthquake that shook the Fukushima Daiichi nuclear power plant was the most powerful to strike Japan since records began.
The Japanese TV station's NHK offices across the country shook.
I couldn't keep standing.
Fires burned across the northern part of the country as gas lines ruptured, and this oil refinery was engulfed in massive flames.
The skyscrapers nearby were swaying like trees in the wind.
The workers stayed calm because they knew Japanese power plants are designed to withstand earthquakes. The reactors automatically shut down within seconds. But nuclear fuel rods generate intense heat even after a shutdown. So backup generators kicked in to power the cooling systems and stop the fuel rods from melting.
High-pressure water-cooled reactors have an abundance of safety systems designed to always keep the core covered with water. We saw the failure of this at Fukushima Daiichi. You know, they had multiple backup diesel generators, and each one probably had a very high probability of turning on at any given time. And they were there, several of them, so that if one didn't, the next one would, and if it didn't, the next one would. Well, the tsunami came and knocked them all out, you know, and that's what's called a common mode failure. At NASA, we were always thinking about how could we have a common mode failure that just trashes our idea of redundancy.
TEPCO had been warned by a government committee of scientists in 2009 that its tsunami defenses were inadequate. It was more than twice the height of the plant's seawall.
The waves were relentless, consuming everything in their path, and watch as it destroys an entire village while still burning fires ride the waves. Hundreds of cars were swept along the current.
Around 20,000 people were dead or missing. The coastline was devastated. Most of the backup diesel generators needed to power the cooling systems were located in basements destroyed by the tsunami waters. The workers had no functioning instruments to reveal what was happening inside the reactor cores.
All of us who had a car were asked to get the batteries.
The scavenged batteries allowed vital monitoring instruments to work again. The levels caused panic.
Pressure was going up and up. Everyone thought, isn't this dangerous?
The rising heat of the fuel rods in the reactor core was creating massive amounts of radioactive steam and hydrogen.
We begin by making these uranium oxide pellets, and we form them into fuel rods clad in this zirconium. Turns out the zirconium, in certain conditions, can be quite reactive with the water that's surrounding the reactor. We have a fuel and a coolant that are inherently incompatible with one another, and that's how we run nuclear today.
As night fell, the Japanese government ordered an evacuation of everyone within 2 miles of Fukushima Daiichi. Radiation levels were now rising.
And this isn't inside the reactor itself. It's in the office.
The engineers suspected something that TEPCO would not acknowledge for months. Nuclear meltdown had begun. The Prime Minister began to suspect that TEPCO was hiding the truth. He decided to go to Fukushima Daiichi himself.
全員がやるべきだと弁当をやるべきだと言いながらなぜ弁当が進まないのか理由が説明できないわけですね。でそれは東電本店が間に入ってるもんですから。
The Prime Minister met directly with the TEPCO engineers. The radiation near the vents was at potentially fatal levels. His orders might condemn the men who went into the reactor to death, but he felt Japan's future was at stake. The workers found the wheel for opening the vent. They inched it open. A thin plume of gas signaled that the pressure in the reactor core was falling. With the venting complete, the workers could focus on getting vitally needed water into the reactor cores. Suddenly, the ground shook. Leaking hydrogen had exploded in the roof of the reactor building, but the reactor core itself was intact.
Iodine tablets were being handed out in the village. I made my daughter take one.
The government widened the evacuation zone, ordering everyone within 12 miles of the plant to flee. The explosion had already set back efforts to get water into the melting cores of reactors 1 and 2. Now reactor 3 was also in meltdown. Another hydrogen buildup meant the reactor 3 housing could explode at any moment. Colonel Shinji Iwakuma and his team's mission was to inject water directly into the core of reactor 3.
Just as we were about to get out of the Jeep to connect the hose, it exploded. Our dosimeter alarms were ringing. Lumps of concrete came ripping through the roof of the Jeep.
The soldiers were now surrounded by radioactive debris. They were injured in the blast, but managed to flee the scene before anyone received a fatal dose. The Japanese Prime Minister ordered a desperate tactic, dumping water on the spent fuel pools from the air. Tungsten plates were bolted to the helicopter to protect the pilots from gamma rays, but the wind was too strong for accurate aiming. The Japanese government ordered a team of Tokyo firefighters to park a truck by the sea to suck up water, then lay 800 yards of hose and leave it spraying into the fuel pool. The route was blocked by tsunami debris. The firefighters now had to lay the hose by hand. After an hour on site, the hoses were finally connected. Radiation levels at the plant began to fall. The hundreds of workers who'd been on standby headed into the plant to lay miles of pipes. A steady flow of water at last started to cool the reactor cores. The workers in the control center began to feel hope.
3 Mile Island, Chernobyl, and Fukushima were all radically different incidents. What was similar at all three was how poorly water performed as a coolant when things started to go wrong. This is not to say that water coolant caused these accidents to occur. It did not. All three accidents were initiated by different combinations of design and operator error. It was water coolant which allowed these errors to multiply and ultimately result in the escape of radioactive isotopes into the environment. At 3 Mile Island, water couldn't be pumped into the core because some of the coolant water had vaporized into steam. The increased pressure forced coolant water back out, contributing to a partial meltdown. At Chernobyl, the insertion of poorly designed control rods caused core temperature to skyrocket. The boiling point of the pressurized water coolant was passed and it flashed to steam. It was a steam explosion which tore the 2,000-ton lid off the reactor casing and shot it up through the roof of the building. At Fukushima, loss of power to the pumps allowed coolant water to get hotter and hotter until it boiled away. These three accidents illustrate the need for a coolant with a higher boiling point than water.
It's only got 100 degrees of liquid range, okay? 0 to 100 C. That's not really particularly impressive. So to jack up water's liquid range, you have to put it under pressure, because that's the only way to get water to go up to 300 degrees C without turning into steam. Super high pressure is one of the basic challenges, difficulties, flaws, whatever you want to call it, of the water-cooled reactor approach. The salts, on the other hand, you have to heat them up to about 300 C before they melt. But once they melt, they have 1,000 degrees C of liquid range. Safety is one of the most important reasons to consider very seriously molten salt reactors. And this is because of the clever implementation that was demonstrated in the molten salt reactor experiment of the freeze plug and the drain tank. And what this simply was it was just a small port in the bottom of the reactor that was kept plugged by a frozen plug of salt. And to keep the port plugged, they had a blower that would blow cool gas over it. So there was a little plug of frozen salt there. Well, if the power went out, the blower turned off, and the heat would melt the frozen plug, and guess what? Psh, the fuel drained into this drain tank, and the difference between the drain tank and the reactor vessel was not meant to lose any thermal energy. The only place you wanted to lose thermal energy was to give it up in the primary heat exchanger. The drain tank, on the other hand, is designed to maximize the rejection of thermal energy to the environment. I'm a mechanical engineer, so all we ever talked about in school was how to, add heat to things and take heat out of things. And one of the hard things about designing a nuclear reactor is design it to not lose any heat while you're running it, because you don't want to lose a bunch of heat in normal operation, but then to turn around and try to keep it cool if something goes wrong. So there are two conflicting things. The great thing about liquid fluoride reactors is you can design them completely separately. You can say, here's my reactor and it's designed to make heat, and here's my drain tank and it's designed to cool in all situations. Better than having what's called deterministic safety systems or engineered safety systems is to have inherent safety systems that will work 100% of the time because it is based on the laws of physics. A cooling system that is completely passive, that does not rely at all on electrical power to manage the decay heat after shutdown. And it's always going to work because gravity is always going to be turned on. Because it was not operating at high pressure, this is a system that was tolerant of extraordinary damage. I mean, if you wanted to go in and jam a projectile through the side of the reactor, the salt would still just drain out now into a pan, but the pan would run back into the drain tanks. Now, in that situation, you're not going to turn the thing right back on again, but it's not going to lead to a dangerous release of radioactivity.
At 3 Mile Island, coolant water which had boiled into steam reacted with the fuel rod cladding to produce hydrogen gas. This led to several explosions. At Fukushima, steam also reacted with the fuel rod cladding to produce hydrogen gas. This led to hydrogen gas explosions at reactors 1, 2, and 3.
Let me diss on water a few more times. It's a covalently bonded substance. The oxygen has a covalent bond with two hydrogens. Well, neither one of those bonds is strong enough to survive getting smacked around by a gamma or a neutron. And sure enough, they knock the hydrogens clean off. Now, in a water-cooled reactor, you have a system called a recombiner that will take the hydrogen gas and the oxygen gas that is always being created from the nuclear reaction and put them back together. It's a great system as long as it's operating and the system is pumping. Well, at Fukushima Daiichi, the problem was the pumping power stopped.
H2O can also react with the fuel cladding to release hydrogen and damage the cladding, releasing radioactive isotopes. These two accidents illustrate the need for a coolant which is more chemically stable than H2O.
A nuclear reactor is a rough place for normal matter. The nice thing about a salt is it's formed from a positive ion and a negative ion. Like sodium's positively charged and chlorine's negatively charged, and they go, we're not really going to bond, we're just going to kind of associate one with another, you know? And that's what's called an ionic bond. Yeah, you're kind of friends, you know, you're...
Facebook friends.
Facebook friends. All right, well, it turns out this is a really good thing for a reactor because a reactor is going to take those guys and just smack them all over the place with gammas and neutrons and everything. And the good news is they don't really care who they particularly are next to. As long as there's an equal number of positive ions and negative ions, the big picture is happy. A salt is composed of the stuff that's in this column, the halogens, and the stuff that's in these columns, the alkalis and the alkaline earths. Fluorine is so reactive with everything, but once it's made a salt, a fluoride, then it's incredibly chemically stable and non-reactive. Sometimes people go, oh, you're working on liquid fluorine reactors. No, I am not working on liquid fluorine reactors. We're working on fluoride reactors, and there's a big difference between those two. One is going to explode, the other one is like super duper stable. I see moving to molten salt fueled reactor technology as a way to get rid of all the stored energy term problems that we look at in today's reactors, whether it's pressure, whether it's chemical reactivity, even the potential of the fission products in the fuel itself to be released. In fluoride fuel, which is what we would use in a molten salt reactor, those fission products are bound up very tightly in salts. Strontium and cesium are both bound up in very, very stable fluoride salts. Cesium fluoride, very stable salt. Strontium bifluoride, another very stable salt. In light water reactors, cesium is volatile in the chemical state of the oxide fuel of a light water reactor. And that's been one of the concerns about cesium release. Cesium would not release from a fluoride reactor at all.
So why are we using water to cool today's reactors? If water coolant prohibits us from completely consuming uranium or thorium as fuel, why did we start using it in the first place? The association between different nuclear fuels and their respective coolants is because some nuclear fuel requires slow neutrons and some nuclear fuel require fast.
There really were three options for nuclear energy at the dawn of the nuclear era. Only one of the materials in nature is naturally fissile, and that's uranium-235, which is a very small amount of natural uranium, about 0.7%. This was the form of uranium that could be utilized directly in a nuclear reactor. Most of the uranium was uranium-238. This had to be transformed into another nuclear fuel called plutonium before it could be used. And then there was thorium. And in a similar manner to uranium-238, it also had to be transformed into another nuclear fuel, uranium-233, before it could be used in a reactor. 9999999. Well, this was wartime. Their plan was to make bombs. They took natural uranium and they separated those two isotopes. They would highly enrich uranium-235 from less than 1% up to like 90+%. Took big factories. It's very difficult to do isotopic enrichment. But this is how they made the uranium for the first nuclear weapon used in war. This was the bomb at Hiroshima. It was called Little Boy. Then they said, well, what can we do with all this junk uranium-238, the 99.3% of it? You could expose it to neutrons, and you could make it into plutonium. Now, plutonium is a different chemical element than uranium, so they can be chemically separated. Uranium-235, uranium-238 are like identical chemically. There's no chemical difference between them. But there is a chemical difference between plutonium and uranium, so it was a lot easier to do a chemical separation of the plutonium you'd made, and that's how they made the Nagasaki bomb, which was called Fat Man. Okay, well maybe we can do the same thing with thorium. Maybe we can expose it to neutrons and we can make it into uranium-233. Uranium will be chemically separable from thorium and we can go make a bomb out of it, right? Sounds great. It's a really bad idea because as you made the uranium-233, you were always making uranium-232. You didn't make a lot of it, you only made a little bit of it. But uranium-232 is much more radioactive than uranium-233. And in addition to that, here's the decay chain that uranium-232 is on. It jumps down to bismuth-212 and thallium-208. And these two decay products put out very, very strong gamma rays. And these gamma rays are just super bad news if you want to go and build a practical nuclear device, because they tell everybody where the stuff is and they kill you. So really quickly they were going, okay, we can work with uranium-235, that seems okay. We can work with plutonium, that seems okay. But this uranium-233 stuff, that's bad news for making a nuclear weapon. So thorium was just set aside.
PG-13.
Well, after the war, they picked up on this again because now they were thinking, let's talk about making power instead of making nuclear weapons. Okay, this is the fast region. This is the thermal region. Squiggly lines and blah, 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 blah. And you could probably tell the entire history of the development of nuclear energy in this one graph. And I'll tell you why. How much energy did the neutron have that you smacked the nuclear fuel with? Okay, how much energy did it have? And then how many neutrons did you kick out when you smacked it through fission? 2 is a very significant number in breeder reactors. You need 2 neutrons. You've got to have 1 to keep your process going, and you have to have another one to convert fertile material into fissile material. Okay, look at plutonium. It's that dip below 2 right there. That's what makes it so you cannot burn up uranium-238 in a thermal spectrum reactor, like a water-cooled reactor. You just can't do it. The physics are against you. And the reality is you do lose some neutrons. You can't build a perfect reactor that doesn't lose any neutrons. So they looked at this and they said, man, we just can't burn uranium-238 in a thermal reactor. It just can't be done. Well, you know, these guys are undeterred. They said, well, here's what we'll do. We'll just build a fast reactor, because look how good it gets in the fast region. Wow, it gets above 2. In fact, it's up to 3. Wow, this is really good. Well, there's a powerful disincentive to doing it this way, and it has to do with what are called cross-sections. These are a way of describing how likely it is that a nuclear reaction will proceed. Look how much bigger the cross-sections are in thermal than they are in fast. How many of these little dots are we going to need to add up to this size? We're going to need a lot. So this is why it was a big deal to be able to have performance in this region of the curve. Those little bitty dots, they're up here in this part of the curve. Okay, this is the fast region. This is the thermal region. Thorium is more abundant than uranium.
All we're consuming now is that very, very, very small sliver of natural uranium.
But this is not the big deal. No, it's not a big deal that natural thorium is hundreds of times more abundant than the very small sliver of fissile uranium. The big deal about thorium is that we can consume it in a thermal spectrum. That's the big deal of thorium, is that it can be consumed in a thermal spectrum reactor.
When you're talking about a thermal spectrum reactor of any kind, you have to have fuel and you have to have moderator. And they're both essential to the operation of the reactor. The moderator is slowing down the neutrons.
And when the neutrons have been slowed down, we call them thermal neutrons, or a thermal spectrum. In a water-cooled reactor, we use water, specifically the hydrogen in the water, to slow down the neutrons through collisions.
The graphite in the molten salt reactor, is that a moderator?
Yes, that's the moderator in the reactor.
Same idea, except we use graphite as the moderator instead of water.
Neutrons go in the graphite, hit the carbon atoms, they lose energy, they slow down.
Now why slow it down? That's the difference when you're going from that little bitty dot to the big dot. That's why you want to slow it down. You want the big dot, not the little bitty dot. A thermal spectrum molten salt reactor has to have the graphite moderator of the core in order to sustain criticality. If the vessel ruptures, recriticality is fundamentally impossible. The drain tank does not have any graphite in it.
If something happens where that fuel drains away from that graphite, criticality is no longer possible. The reactor's subcritical fission stops, and there's no way to restart it without reloading the fuel back into the core. This is such a remarkable feature, and it really is unique to to having this liquid fuel form and to having something that can operate at standard pressure. You can't do this in solid fuel. If you do this in solid fuel, it's called a meltdown. That's bad.
Now, in a fast reactor, on the other hand, you don't depend on moderator. You put enough fuel in the reactor so the criticality is possible even without moderator. In those scenarios, if there's a drain or a spill or something, you need to be careful about what geometries it could get into, because recriticality is not, from first principles, impossible. It may be impossible in the design you've designed, but that becomes design specific. Whereas in thermal reactor, it is just impossible. Outside of the lattice of moderator, you can't have a criticality set up. The thermal region, look who's doing the best. Look at uranium-233. Look at that. Okay, look at plutonium. It's that dip below 2 right there. You just can't do it. The physics are against you. But uranium-233, on the other hand, okay, yeah, it gets a little better in the fast, but dang, it's still pretty dang good right here in the thermal. Big targets, a lot easier. This fact was not well known probably till about the 70s. There was some data that indicated it, but there was enough uncertainty even as late as 1969 that the Atomic Energy Commission did not feel like it was a safe bet to go with thorium. Everybody who was pushing thorium said, we like thermal, this is the kind of reactor we want to build. And everybody who was pushing plutonium said, no, we want a fast reactor, that's the only way to do it. And so what happened is they put resources into the plutonium breeder reactor almost from the get-go. They built the experimental breeder reactor 1 in 1951. So this was the first reactor that made electricity. 4 little light bulbs here.
This is a mock-up of the core. This size was giving off a megawatt of thermal energy.
How tall is this? How many meters?
8 inches.
This is actual size?
No, it's scaled down. No, that's full size. EBR1.
This was a breeder reactor. It was designed to convert plutonium into energy while making new plutonium. This was not a light water reactor. This predated the light water reactor by years. It was a fast breeder. This is 1951. This is a Gen 4 reactor. No kidding. Early nuclear pioneers like Enrico Fermi and Eugene Wigner saw the future quite a bit differently. Fermi believed that because of the performance of plutonium, and especially because it could have a substantial breeding gain, in other words, it could make more fissile material than it was consuming, that we should really focus our efforts on the fast breeder reactor. Eugene Wigner, on the other hand, looked at these same pieces of information and reached a different conclusion, which was that thorium was a superior fuel and that it should be realized in a thermal spectrum, in a thermal breeder reactor. And this opened up a number of possibilities with coolants and reactor configurations. But thorium, in another way, was a rather unforgiving fuel. It did not have a great breeding gain like plutonium had the potential in the fast spectrum. You had to make sure that you were very careful and conserving of your neutrons. You couldn't waste a lot on losing neutrons to structural materials or losing them to leaks out of the reactor or losing them to absorptions in the daughter products of fission. And thorium also had another challenge. It took about 40 days once it absorbed a neutron to turn into uranium-233. There was a time delay there between when it absorbed a neutron and when it became new fuel. Fermi wondered how it would be that thorium would overcome this problem of the delay from when it absorbed a neutron to when it became new fuel. And Wigner had already seen a possible path forward, which was to do something rather revolutionary. Build a nuclear reactor out of liquid fuels rather than out of solid fuels. I believe part of this came from Wigner's educational background.
He was the only person, or almost the only person, who combined great skill as a nuclear physicist with great skill as an engineer. Wigner, of course, was a chemical engineer by training. He was the only one who commanded both of those attributes. And so he was able to see both the engineering and physics aspects.
He was a chemical engineer by training, and he knew that in chemical processes, the reactant streams are almost always liquids and gases. They're fluids. And in fluids, a complete mixing is possible, and completion of the various chemical reactions are possible. He looked at the nuclear problem and wondered if the same principle might not apply. With a fluid-fueled reactor, it would be possible to isolate protactinium-233 as it was formed and to allow it to decay and prevent it from being destroyed before it could complete its transition to uranium-233. Wigner was not successful in convincing the bulk of the nuclear community to take the thorium approach. They, by and large, said, we're going to go the plutonium route. And one of the reasons why was they had developed a great deal of understanding about plutonium from the weapons program. They had made the stuff, they had worked with its chemistry, they'd made fuel out of it. They go, we get this. Thorium, we haven't really messed with thorium. You know, it would be like starting over. So that propensity there was to go and do what you already knew how to do. And the plutonium was so much better developed than the thorium. So Wigner was not terribly successful in making converts in the nuclear community. But he did make one convert, this guy, Alvin Weinberg. He was his student during the Manhattan Project.
Of course, I had heard about Eugene Wigner as this great, wonderful physicist. I gradually became his assistant in charge of the nuclear design.
And Weinberg got it. He got the big picture. He got, we need thorium, we need thermal reactor, we need liquid fuel. I see it. I see what we got to do.
We visited with Mr. Rosenthal after we met with you. He spent time in Washington, D.C. with Milt Shaw. And that Milt actually had quite an affinity for Knoxville and Oak Ridge. But he wanted Alvin Weinberg and Oak Ridge to get on the fast breeder funding wagon, and that Weinberg wanted to stay on with thorium and molten salt.
Well, it was pretty obvious that Shaw was completely convinced the LMFBR, with its sodium cooled system, was going to be successful. If we have a winner here, why spend money on what we know is going to be the loser?
So everyone was so just euphoric about the idea of the fast breeder.
Well, that's the way it appeared to me.
The Baroness has got a bunch of people over there from GE saying that you got to go build the fast breeder.
But the Russians are building them, and we built a couple of them. We had a couple problems with them, actually. But in principle, I guess you can go that route, but relative to a molten salt reactor, you've got a lot of fuel cycle infrastructure that you wouldn't need if you went to the molten salt reactor. So I wouldn't do it. I wouldn't build fast breeder reactors if I were the person deciding.
In the U.S. nuclear Navy program, they started out with 2 reactor systems, one water-cooled and one sodium-cooled. And it didn't take very long for the Navy to decide that they didn't want to deal with sodium cooling.
They built a reactor and put it in a sub, and they ended up cutting the reactor out of the sub and putting a LWR in it.
They became disenchanted with sodium cooling rather quickly.
What happens if there's a leak? Sodium reacts with the air and the water.
Well, you haven't got air next door to your sodium surfaces. It's inerted. You can handle it with freeze packs if you like. You're not getting stuff from the core getting out into the air. People normally can't walk around the surface of this. You know, if I've just got a little tiny thin pipe that can't let very much flow out, you'll have a different access availability than a big sodium pipe that's 2 feet in diameter with several hundred pounds per hour flowing through it.
What about the sodium?
Well, no, see, they're not dumb.
You got it, brother. You got it.
Well, what's their answer? What's their answer? Fire suppression system.
If you've got a hot liquid combustible metal in your iPhone, lithium,
yes.
Why are you allowed to walk around with it?
Because lithium is in a stable compound. It's not pure lithium.
Yeah, I'll show you some YouTube videos of lithium not being in a stable compound.
Yeah. If I take a lithium battery and I expose it to air, it's not immediately going to catch on fire.
Sort of uneventful. Oh well.
A lithium battery catches on fire because it shorts out. It shorts out.
But the point is, like, there's a known history of lithium accidents, which are pretty bad, you know, and we don't ban them, but you know, I agree. I don't think the IFR was the best possible solution in the world, but they did have a history of proving that it could shut itself down.
Right.
You know, with total plant blackout.
Simulated a complete blackout so the power was lost to all cooling systems.
For fast sodium reactors, you've always got two separate loops.
Okay.
The primary gets radioactive.
Oh,
because
your
it's in
clean
the
sodium
core.
and your dirty sodium.
Yeah.
Okay,
So
I
then
gotcha.
it's the clean sodium that goes to the steam generator.
Okay.
So if you get a failure in the steam generator wall, you haven't got radioactive sodium.
I got that. Yeah. So this thing here, this loss of heat sink test would be turning off the power to the secondary, so you're not drawing the heat out of the core. Is that what or not the heat is changing?
You would shut down the tertiary, the water system.
The tertiary, okay. And so this other one, loss of flow test, is that shutting down the intermediate?
The loss of flow test is shutting off the pump. Just turning off the primary pump in here.
The pump for the primary sodium.
Yeah, it turns off the pump that's somewhere in there.
So these two tests are turning off the primary and turning off the tertiary.
Yeah.
Okay. But at all times, the core was still bathed in sodium.
Mm-hmm. The sodium's there the whole time.
Okay.
The only thing you're doing is you're also doing it without scram.
Right, without control rods going in.
Without control rods going in. This gets so warm, the fuel assemblies expand, the pins lengthen, they expand sideways, pressurizing up against the core rigidity structure.
Achieving a strongly negative temperature coefficient in a thermal reactor is a much more straightforward proposition than in a fast reactor. It can be done, but it's easier to do in a thermal spectrum reactor. There's a lot of options. A lot of those options are connected with the process of moderating neutrons. So you change something about that process and it helps you achieve a strongly negative temperature coefficient.
The fuel expands, the clad expands, the fuel assemblies expand, the core support structure expands, the core plate underneath expands.
Gotcha.
This is at the molecular level in the salt reactor because it expands. The salt expands.
That's why I wanted to get
the same thing, except this is done at the physical level, and so in the salt it's easier to have this happen.
That's why I wanted to drill down and get some questions answered. But great, that was very informative. Thank you, sir.
The trouble is these tests were done about 2 weeks before Chernobyl.
Yes, that's right. That was
so
amazing.
No one even knew about this, which is a shame. Bob.
So my question was, this was not commercialized, right?
We were going to, it was called Clinch River. I was working on Clinch River, and then Al Gore, who thought that plutonium is nasty, wicked, and evil, and we shouldn't have anything to do with it, persuaded Clinton to shut the program down.
I've actually been to the site where the Clinch River fast breeder was supposed to be built. I hopped the fence and trespassed on federal property and walked out to the river, and it's an empty field.
The country thought the liquid metal fast breeder reactor was going to be the future. We've now done 3 of them. 2 have had unintentional core melts. The last one happened in 1972, where the plant manager had to call the mayor of Detroit and say, prepare to evacuate Detroit.
Well, how is that Detroit reactor different from here?
The Enrico Fermi fast breeder reactor was built by Detroit Edison, made with metallic fuel like this. Actually, it went online about the same time as this one. The AEC said, well, what happens if you get a meltdown? So they said, okay, we'll put some zirconium plates underneath. The trouble is, when they put them in, they only tack welded them, and the vibration tore one of them off and went up and flattened underneath, blocked off the sodium. So there's a significant meltdown, but they cleaned it all up. Milt Shaw, insisting on oxide fuel for Clinch River, wouldn't help give them some money to buy another core load. For want of a couple of $1 million, the plant went down.
Unbelievable. Good old Shaw, he's the guy who really is responsible for our trouble.
Milt Shaw is quite infamous in the molten salt community. I had no idea until I read Plentiful Energy. Milt Shaw is infamous to the IFR crowd as well. Boy, he was just infamous to everybody.
The folks who were in support of Clinch River fast breeder reactor had very sharp elbows. Guys who were working on the integral fast reactor have just as much heartache with the focus on the oxide-fueled loop reactor at Clinch River as you do. I mean,
I agree.
Fast reactor
you're
does not equal
right,
fast
Rod,
reactor, right? Sodium loops with pumps. That flavor, that was the project. And, people who wanted to do metal fuel in a pool reactor, they wanted to do molten salt, they wanted to improve the light water reactor, they wanted to prove that the light water reactor could do breeding as well. All of those projects were put on back burners or defunded completely.
Making solid nuclear fuel is a complicated process, and we extract less than 1% of the energy from the nuclear fuel before it can no longer remain in the reactor.
Kirk makes a big deal about, the fact that he wants to, use thorium because it's 200 times better than using uranium, but, using uranium is about 10,000 times better than using oil. So let's make the big jump first. The nukes, though, need to stop fighting amongst each other and compare their power plants to the real competition that holds 85% of the market, which is the fossil fuel companies.
Nobody saw the light water reactor as the machine on which we would power our civilization using nuclear power for thousands of years. The only question is which breeder and how fast do we get to it? I mean, I got a 1962 report to the president, and right in there it states this is a stopgap technology. I think these early nuclear pioneers would be absolutely floored to show up today in our nuclear world and go, oh my gosh, you're still using light water reactors? I mean, come on, guys. We should have seen more technology advancement by now. We should have seen something better.
Pressurized water reactor has to take 2,000 psi. Which is a really thick pipe. It's typically 4 to 8 inches depending on the diameter of the pipe.
We're doing new things with light water. The core, the pumps, the control rod drive mechanisms, the steam generators, the pressurizer, all in one steel pressure vessel. No piping penetrations in excess of about 3 inches in diameter. I'm working on that exact reactor.
The light water reactor is still the most efficient, safest energy source we have on the planet right now. And it's a real thing, and we have a big worldwide fleet of these things. It should have been bigger, but we have like 400 some reactors running. All we are saying is that in the very near future, we could have something that's even yet safer and even yet more efficient. If someone said, well, all you can have are water-cooled reactors of some type or a vast array of fossil fuel and so-called renewable energy, I'd rather all my energy was created by light water reactors any day.
Nuclear right now means water-cooled reactor, uranium oxide solid fuel, poor fuel efficiency, and steam turbine. That's what nuclear power means right now. How do you tell people this isn't your father's nuclear, or this is different?
It's a much better way to utilize our resources in every way.
Molten salt reactors reignited my passion in nuclear because to me it solves the waste problem.
People look at Fukushima Daiichi and they go, is this the end of nuclear power? And I go, no, it's not the end of nuclear power. It's like, there's a zillion other ways to do nuclear power. I think this is the best way. Maybe I'm wrong though. Maybe there's a better way. I've been looking for it. I tell anybody I got a standing invitation. You can figure out how to do this better. I will be happy to go do whatever it is that's better. I'm always looking for it.
Show me a system that is superior to a molten salt reactor, and I'll say yeah. But to this day, there isn't one.
It's not based on nothing that people have spent their careers and many, many successful long-term tests. This is not a theoretical technology. This is a proven technology that just needs to be commercialized. It's just by dint of a solid fuel supply chain having gotten started that we don't have molten salt supply chain in place.
While molten salt reactors allow previously unattainable levels of passive safety, this does not mean that pressurized water reactors present any greater danger than coal, solar, wind, or natural gas. Despite 3 Mile Island, Chernobyl, and Fukushima, existing nuclear power is already the safest form of energy available to mankind. This is because every source of energy has risk associated with it. Molten salt reactors and other modern reactor designs such as the AP1000 minimize the impact of any error by improving passive safety mechanisms. Any incident at a newly constructed reactor is much less likely to disperse radioactive isotopes. But the key to reducing errors in the first place is having a well-regulated industry.
Hey, Barney.
Yo.
Open 14 and 15.
You can't do that, Jack.
Open them, Barney.
Jack, you can't do it. The book says
Well,
you can't do it.
We're almost up to the steam lines.
It just might be a feed water leak.
Which valve?
Can't really tell.
Shut the isolation valves.
You're gonna need that feed water later.
You want to go down there and do it by hand? Do it.
Jesus Christ! Water, Barney, give me seawater! God damn it!
We'll probably never know the full extent of how badly Soviet nuclear power was managed.
I sat before the world in Vienna and blamed those young men at the controls. I made no mention of the role I'd played in their ignorance. I did not speak out.
Valery Legasov's suicide caused shockwaves throughout the Soviet nuclear industry. Design flaws in the graphite tips of Chernobyl-type RBMK reactors were finally admitted to and changes hurriedly made.
But we do know that Japan's nuclear industry has seen a steady stream of fatalities. This does not happen in France. This does not happen in Germany. Over a 10-year period, United States nuclear power was responsible for a single fatality, from 2003 to 2012. A uranium miner died when a support beam collapsed. Because every single source of energy has caused at least one fatality during this period, and we know how much electricity was generated by each energy source, we can express how safe each form of energy is as a quantity of watts per human life. For nuclear power, because there was only a single fatality, we divide by 1. Almost 8 million gigawatt hours of electricity per human fatality. The next safest form of electricity is hydroelectric power. Hydro produced about half as much electricity as nuclear, for which 6 people died during that same period. Next is natural gas. We've all seen natural gas explosions on the news. Somewhere between 26 and 27 people were killed during that same 10-year period. It is a fractional number because the natural gas was dual use. Only a portion of it was for generating electricity. Now that we're burning fuel, we have air pollution to consider as well. 144 fatalities can be reasonably associated with the pollution caused by burning natural gas over that same 10-year period. Even with the cleanest burning fuel, air pollution kills more people than explosions. Natural gas gives us about 52,000 gigawatt hours per human life. The safest renewable is wind, about 21,500 gigawatt hours per life. Wind fatalities are due to maintenance. Just like nuclear power, this could easily go up or down depending on how the industry is regulated in the future. But there are a lot of turbines, all requiring regular maintenance, each one producing a moderate amount of electricity. To improve the watts-to-life ratio and try to make it as safe as nuclear power, it is reasonable to expect the cost of wind turbine maintenance to go up, driving up the cost of wind power. 27 people died maintaining wind turbines over that 10-year period. Natural gas comes out ahead of wind because it produced far more electricity. Solar is 2.5 gigawatt hour per human life. There are a whole lot of rooftop solar panels, and each one only produces a tiny fraction of the energy that a wind turbine does. Of all renewable energies, photovoltaic solar power is the least competitive in terms of price, but it also offers the biggest opportunity for improvement if panels can be made more efficient. Such an improvement in panel efficiency would also improve solar's safety standing, since more watts could be generated for the same amount of maintenance. In the United States, from 2003 to 2012, average number of watts generated per fatality is 300 gigawatt hour per human life. How is our average so much lower than any number we've looked at so far? Because of coal. Let's not forget electricity produced by burning coal. Coal mining killed 298 Americans over 10 years. Coal mining fatalities dwarf all other forms of accidental death in the United States. But the big numbers are in air pollution. In 1 decade, burning coal has killed over 130,000 Americans, largely due to the release of tiny solid particles that we inhale, causing respiratory illness. Burning coal also exposes us to mercury poisoning. This is how America's consumption of electricity kills people. by coal. Every other source of electricity is safer per watt. On the other end of the spectrum, no other source of power has the potential to meet all of our electricity demand with such a small impact on human lives, disrupted ecosystems, and future costs projected from greenhouse gases being pumped into our atmosphere. Nuclear hardware is shielded from the degrading effects of sun, wind, and rain. All safety systems are focused on a small area and a handful of highly trained individuals.
Nuclear has the advantage that the amount of energy sort of per atom is about a million times better than coal or natural gas. So you start with this huge advantage, and yet given the complexity of the plants and the things you have to do, you more than wipe out your million-for-one advantage. And today's nuclear plants are fairly expensive, at least the way they're built outside of China. So they're pushing the state of the art, and they're standardizing designs and things like that. So nuclear is one of the directions that we should innovate in. Nuclear innovation stopped in the 1970s. We basically have this sub-design thing that was put into Shippingport for the first power generator, and we basically built 400 of those that are all kind of custom, but not in any interesting way.
The reactors used to, in the United States, had like 40, 50% uptimes. I mean, they were horrible. They standardized everything they could, pumps, valves, motors. I mean, that's how crazily one-off these plants were. They would get like custom nut and bolts, for like the pressure vessels.
Well, part of that is due to 3 Mile Island, because after 3 Mile Island, they realized that training was that good and was not uniform across the companies. Kind of forced all the companies and utilities to get together to share their training and procedures. It made a huge difference.
Yeah, 3 Mile Island, what an indictment how poorly managed the industry was back then.
Choosing nuclear power does not guarantee safety. It is possible to make an unsafe reactor, to staff it with poorly trained individuals, and it is possible to respond to the release of radioactive isotopes by doing nothing at all to protect the public.
Well, the only equipment we have to measure it are the control room Geiger counters, and they're reading 3.6 Rentgen per hour.
Well, I thought that bad, is it? I mean, 3.6.
But the scale only goes up to 3.6, and it's off that scale.
It could be 3.6.
Yes, it could be 3.6.
Zakov, I have no intention of telling Moscow it's worse than it is, okay? If it says it's 3.6, it is 3.6.
The other 5 reactors in the Fukushima prefecture were built just a few years later, and all the reactors at Fukushima Diani, none of them had significant damage. We figured out how to prevent that problem sometime around 1971, 72. The one thing that the Japanese didn't do was go back and fix the early systems, because they thought, we've operated the plants for 40 years and it's not been a problem before.
We have 3 standout examples of what not to do, and decades of safe operational experience from hundreds of nuclear reactors around the globe to learn from as well. What choices can we make today so that nuclear power can be even safer?
Very few people understand all the options that are available in nuclear energy. It's a complicated subject. It's a subject that is actually quite new. The first chain reaction experiment was December of 1942. My mother was a teenager in 1942. She's still alive and kicking.
This is the only part of the energy business that has anything close to a Moore's Law capability for improvement. We're still at the very early stages of figuring out how best to put that energy inside the atomic nucleus to use.
At the time when society had its most optimistic view of science, it had the view that if that was the form it took, then it must be the right form. But we still have this view that society can't shape technology, that the form that the technology takes is the form we must accept. What science and technology gives you is a range of possibilities, and those possibilities can take you in any number of directions.
I'm Bert Wolf. I had General Electric's Peaceful Nuclear Power Program.
General Electric and Westinghouse took the simplest form of nuclear reactor, originally designed for submarines, and redesigned it on a gigantic scale, offered to power companies at knockdown prices.
We would sell one at a time, and each time we sold one, we'd have a celebration. I can recall when we'd have meetings and someone would come in and said, we sold a plant to somebody, and we'd all stand up and shake hands and go out for lunch and have wine and toast each other. It was a great celebration. So we began selling these by the tens, so it became a real business.
The history of nuclear power is a history of political and economic and social decisions being made about a technology. And the key decisions weren't made by the technologists. They were done in the business realm.